Well, good morning, everyone. My name is Ken Baldwin. I'm Director of the Australian National University Grand Challenge Zero Carbon Energy for the Asia Pacific. And it's my pleasure to welcome you all here today to the third of our State of Energy Research webinar series presentations called Preparing Electricity Networks for Extreme Climate Events, Learnings from California and Texas. This webinar is a joint activity of the Energy Research Institutes Council for Australia, chaired by the Monash Energy Institute for a second year. And that is jointly hosted with ourselves at the Australian National University's Institute for Climate, Energy and Disaster Solutions, otherwise known as ICEDS for short. Just to let you know, the webinar will commence with a couple of presentations plus some discussion, and we'll go for about 3/4 of an hour or so. And then after that, we will have the opportunity for everyone to participate in question and answers. And we will do that using the Q&A function on the Zoom link. So if you have some questions, please place them up there. We will record this webinar, and indeed we will provide it to the ERICA website and the ERICA YouTube channel after we've done some post-production work, and it'll also be available under the ANU ICEDS YouTube channel and webpage. But before proceeding any further, I would like to acknowledge the First Nations people on whose lands we meet wherever we are in the world today, and to acknowledge their elders past, present and emerging. And at this point, I would like to introduce the current chair of the Energy Research Institutes Council for Australia, Ariel Liebman at Monash, to say a few words about the ERICA State of Energy Research webinar series. Over to you, Ariel.
Yeah, hi everyone. Thanks, Ken. Right, so as Ken mentioned, I'm Ariel Liebman. I'm an Associate Professor in Data Science and AI at the Monash Faculty of IT and Chair of ERICA for this year. And I'm also Director of the Monash Energy Institute. And ERICA itself is a very exciting initiative that we thank Ken for kicking off 2 years ago. And it's really an organization that seeks to provide a much more collaborative and inclusive research environment in Australia for all the universities and other institutes that are working in the energy transition space. And so we hosted 2 years ago, I think it was now, Ken, 2019, the State of the Energy Research Conference. And that was a really exciting kickoff for the council, and the council is represented by 12 institutes and universities from all around the country. I encourage you to go to our website, erica.org.au, and you can find out a little bit more about our mission and our vision and the people in your own university who are involved in ERICA, and encourage you to encourage them to look at ways of collaborating. We have some national initiatives now. The Australian Council of Learned Academies is working on a national energy transition research plan led by such eminent people as Ken and Drew Clark. And so we will be seeing some of this outworking throughout the year. Last year, instead of a conference, we had a webinar series, and we are continuing this as part of that. And then going forward to later this year, we will be hosting another State of the Energy Research Conference, and encourage everyone here to come, industry or academics. And it's going to be a forum for discussing how we can all work together to get the next generation research programs and activities going. So with that, I'm very happy to jointly with Ken will do his own opening, but Thank you very much for to our speakers. I'm very much looking forward to hearing what the view from the US is, as well as our discussants, Liz and Anna, give the Australian perspective. So with that, thanks very much, Ken, and over to you.
Great, thank you, Ariel. And so without further ado, I'd like to introduce Dr. Fereidoon Sioshansi, Perry for short. Perry is president of Menlo Energy Economics, which is a consulting firm based in the San Francisco region in California, and he has more than 35 years of experience in the electric power industry. Perry advises on strategies to respond to the rapid transformation of the energy sector, including to utilities, energy-intensive industry, innovators, startups and companies that are engaged in electricity delivery supply chain, regulators and policymakers. So a very broad range of engagements indeed. So thank you, Perry, and I'll now hand over to you to start the presentation.
Thank you very much, and I guess it's noon your time. It's 7 p.m. for me in San Francisco, and I'm guessing it's 9 p.m. for Ross. So good to be in good company again, and I see 100 people at this point. It's a fantastic turnout. So thank you, Ariel and Ken and colleagues for doing a fabulous job of promoting this event. It's certainly exciting. We're happy to share with you, Ross and I, a little bit about what happened in California and Texas. The plan for, at least as I see it, is to, to give a brief introduction into what happened in California mid-August of 2020. Many people have forgotten about that. Certainly after what happened in Texas, it was a small hiccup in California compared to what happened in Texas in mid-February. And we're going to mention, briefly a little bit about what happened and why. And also I'm going to talk a little bit about similarities and differences between California and Texas. But before I move on, I think ERCOT actually had another kind of scary spell just earlier last week, I believe, on the 13th of April. There was another cold spell, at least for Texas. And the system operator, from what I understood, misjudged the demand by 3 gigawatts. And this again happened at a time where a lot of the plants were offline for maintenance, because this is normally a shoulder period. So there was some reports that in fact it was a close call. Maybe it wasn't so bad, and Ross can tell us how close it was to dangerous territory. Anyway, after we're done, we turn it over to the 2 local experts to talk a little bit about what's happening in Australia. The message, I think, is, since we're talking about climate, this first slide is from last August. These were incredible wildfires. I guess you call them bushfires. We call them wildfires. It's the same thing. And this summer promises to be perhaps just as bad as last year. So we had on top of the heat waves and everything, it was just tremendous problem with the fire. So climate in California, I can certainly tell you, the years that I've been here, is summers are getting warmer and longer. In many parts of the world, 4 or 5 inches of snow is nothing to write home about. But in Texas, when it gets, if it gets serious amount of snow, everything comes to a stop. And this was pretty unusual, I guess, for that part of the country. Again, Ross can tell us, but he told me that he was without power for something like 60 hours. So it's pretty bad when it's cold and you don't have power. The next slide is from New South Wales, and you probably know more about this than me. There were serious flooding that affected parts of New South Wales. So the message I'm trying to get across is that it seems to me, I'm an economist and not a weather expert by any stretch of imagination, but it certainly seems like weather is becoming more abnormal, let's say, and we're getting more of these extreme weather events. They're happening more frequently and they are more pronounced. And of course, it has a big impact on electricity supply and demand, as we will talk about. I will briefly talk a little bit about the California Independent System Operator, what happened in August of 2020. And I think, as I mentioned, this was embarrassing, but the damage was limited, certainly by comparison to what happened in Texas, which was significant. Many of you have probably seen this chart many times, as everybody seems to show it, at least in the US. This is the famous California duck curve, and it shows the daily fluctuations in net load, which the California Independent System Operator sees. And you can see that what happened in 2012 and every year since then, the belly of the duck gets bigger because of the sun in the middle of the day. And when the sun sets, of course, the independent system operator has to come up with something like 13 to 16 gigawatts of replacement power to substitute for the sun after it sets. And the next slide shows this in a different way. And basically the blob that is orange is solar energy, which disappears at the end of the day, and you have to replace it over a short period of time with something else. And the something else is fossil-based or imports from other states. We don't have a lot of storage at this point. So the system operator has a very difficult time during this ramping period where the solar goes to zero and has to be replaced with something else. And essentially what happened in California, they fumbled the ball during this critical period. So why did this happen? Why was this particular ramping more difficult than any other day? Well, one reason, and at least in my view, the most important reason, was that California and much of the Western US, in fact, was undergoing an extreme heat event. And as you see in this map, 32 million people in portions that are colored were subject to extreme heat. And so normally what happens in California, being a long and narrow state, you might have heat in the north or in the south or in the middle, and not so much anywhere else. But in this particular case, the whole of the state plus many of the neighboring states were all suffering from extreme heat, and it went on for several days. And as you can see in the next slide, we had another heat wave back in 2015. That's the curve in the blue. But you can see that it only spiked on 2 days, which were separated by a week or so. Whereas the episode in 2020 was higher temperatures, and it lasted for an extended period of time, at least extended by California standards, not by Texas standards. And what happened during this period, the average temperature across all of California was about 10 degrees Fahrenheit above normal. Now, that is on top of what would have been a hot August day. So you add 10 degrees Fahrenheit to top of an existing hot August day, and you get enormous strain on the network, which is essentially what happened. So how big was this event? Well, on this slide, you can see the 3 large investor-owned utilities that serve most of the customers. So something like less than 500,000 people were affected. And the duration of outages in California lasted from 15 to 150 minutes max. And moreover, what is interesting about California, and this I think Ross will probably comment on this, the shortage was 1 gigawatt in a system of about 40 gigawatts. So had we have demand response of equivalent to 1 gigawatt, this whole episode could have been avoided. And because the duration was relatively short, batteries and demand response would have made a big difference. But I think as we will hear from Ross, when you have shortages of 20 gigawatts over 4 days, batteries don't help, demand response, the traditional types of demand response don't help. So California, as you see them on the coast, California Independent System Operator handles the part that is light orange. These other areas, the neighboring states have joined in what is called the energy imbalance market, which is a real-time market. So the attempt by California ISO is to bring in diversity of resources, renewable and otherwise, from a much broader region to help out California, which is 40 million people. It's more than all of Australia in just this one state. So it's the 500-pound gorilla in the Pacific West US. So what happened and why? I think the short answer is it was unusually hot. This is what created demand that was more than was normal for that type of August. And I think all the analysis that I've seen really suggests that California ISO, having known and having worked with this duck curve issue, somehow managed to fumble on that critical day. Now, as you can see in the slide, there are some similarities to Texas. I think in both cases, we can say it was climate induced. In one case, it was extreme heat. In case of Texas, it was extreme cold. In case of California, solar, which is the big player, was really not to be blamed because it performed as solar does. Sun comes up and sun sets, and we know how that works. In Texas, I think, hopefully, Ross would agree with me that wind was also not to blame. It was mostly the thermal plants that did not do well. So what actually went wrong, and this is part of the reason we're talking today. Another interesting thing about the two states is that both of these markets are energy-only markets, similar to what you have in NEM. So there's no capacity market. In California, we have a regulatory mandated resource adequacy, RA, mechanism, which tries to, provide sufficient capacity for days like this. In ERCOT, the market primarily relies on a very large price cap, as in Australia, to provide incentives for generators to be prepared and ready and make money, hopefully, on those types of days. But as this particular episode showed, neither of these systems performed adequately, or at least as intended. And I think Ross is going to make some comments on that as well. Fortunately, in case of California, the outages were limited, both in terms of scale and duration. In case of Texas, the outages were extensive and long. And I think state of Texas is now paying for that financially as well as politically. It's a big issue. And the next slide, I'm going to go through these very quickly. Basically shows what happened in ERCOT with load and resources and the shortages. And the next slide also shows the performance of different kinds of resources. All of these are available from a report that was published by a joint report that is available at California ISO website. And the last slide, which is the lead-in to what Ross is going to talk about, is the market in Texas was allowed, the price was allowed to reach all the way to the $9,000 per megawatt hour and essentially stay at that level for very extended period of time. And that's one reason for some of the bankruptcies and outrageous bills that some customers on real-time prices received and so forth. So with that, I've exhausted my few minutes and I'm going to stop at this point. Thanks again, and back to Ken.
So thank you very much for that, Perry. And it's now my pleasure to introduce Emeritus Professor Ross Baldick from the Department of Electrical and Computer Engineering at the University of Texas at Austin. So Ross's research involves optimization, economic theory, statistical analysis applied to electric power systems, and particularly in the context of increased renewables and transmission. Ross, I believe you did your degree at University of Sydney, and you are now a fellow of the IEEE and a recipient of the 2015 IEEE PES Outstanding Power Engineering Educator Award. So over to you, Ross.
Thank you, Ken, and thanks very much to Perry for the lead in here. I definitively will echo several of the things that Perry mentioned and concur with him. I do want to talk a little bit about the weather context and how the electricity demand was significantly affected by it. Move on to the rolling blackouts, and I'll certainly mention my personal experience, as Perry mentioned. The reason for the outages and the blackouts, fairly obvious at one level, but a lot of forensics needed at another level. And I will also talk about wholesale market prices and some of the aspects of relevance to Australia. So I think anyone would have a stereotype of Texas that is hot, and Texas definitely has high summer temperatures. We have many days every year above 38 degrees Celsius. We have tens of consecutive days each year above 38 degrees Celsius, which is pretty hard to take without air conditioning. Having said that, because it's expected that it'll be hot, the generation plant is generally, and electricity assets generally, are pretty well weatherized for the summer. Let me call that summarized. But what may surprise people is that Texas is occasionally extremely cold as well. And we've had extreme cold once a decade on average since at least 1899. But because that's a much less common occurrence for various reasons stemming from that, the gas infrastructure, natural gas, which supplies a large fraction of our generating stock, the electric generators themselves, and the water infrastructure for cooling water is less well weatherized for the winter. In particular, I might say that it's less winterized. The last time we had a big cold event was in 2011. There was a major report that came out of that. There were a bunch of recommendations. It's not clear at this point. As I said, I think we need to do some more forensics on this. It's not clear at this point how many assets were winterized as per the recommendations in that 2011 report, but it looks like many assets were not. Certainly many assets in the natural gas infrastructure were not. As well as the supply side, effects on the supply side, extreme cold has a big effect on the demand side. And this year was quite unprecedented in many respects. So prior to 2021, the winter peak has always been lower than the summer peak. And because Texas is hot, it's a summer peaking region. The summer peaks have been bigger than 70 gigawatts since 2015. By the way, as Perry mentioned, California peak with a lot more people is on the order of 40 gigawatts. So we have a large air conditioning driven load, like Queensland, for example. And since 2015, it's been greater than 70 gigawatts. It's currently around 75 gigawatts, summer peak. The winter peaks, which I've got on the graph here on this page, are more variable. And as you can see, if you look at the blue bars, have always been below 70 gigawatts. The actual delivered peak of power in 2021, at least so far for the winter, was 69 gigawatts. That was just before the demand started to take off and the blackouts started happening. So that red bar there actually goes up to about 74 gigawatts, which is what was predicted based on information about feeders and weather as to what the peak would have been in the February event had there not been curtailments. In other words, had there not been blackouts. And as you can see, that 74 gigawatts of peak is literally off the charts from the perspective of our historical electricity consumption in the winter. So although I think there is some blame in terms of forecasting, particularly since we should have anticipated that once in a decade there was going to be something extreme, I think it's probably fair to say that this was an unprecedented event that could not have been fully predicted in advance. Well, there had been, as of up to Sunday evening before the blackouts, outages of all sorts of generation assets, nuclear, gas, coal, and wind. And then blackouts, demand went up, there was rolling blackouts called, and there were further outages during the blackouts. And furthermore, the natural gas supply to the gas-fired generation, about half of the capacity in ERCOT is natural gas, or half the capacity is natural gas. That gas supply was also reduced. So over the Monday, Tuesday, Wednesday, Thursday, mid-February onwards, there was about 35 gigawatts of forced outages and derates. Nameplate capacity is 107 gigawatts. Of that, about 25 is wind, and there's a few gigawatts of solar. So one wouldn't normally think of that as being able to deliver fully, and indeed neither the wind nor the solar was expected to be at its full rating at that time. So that 107 probably exaggerates what we can think of as reliable capacity. But with the 35 gigawatts of forced outages, resulted in up to 20 gigawatts of load shed. As Perry mentioned, ERCOT is a bit of an island, but it's an island that is partly connected to the rest of the world. So in fact, the winter weather was pervasive across the interior of the United States. And in fact, the surrounding regions around ERCOT also had rolling blackouts. Given that they had rolling blackouts because of a lack of supply, they were also curtailing their exports to ERCOT. So imports to Texas were also reduced during this period. We had a bunch of distribution feeders outaged as part of, quotes, rolling blackouts, although in many cases they were not rolled. So we had distribution feeders outaged almost continuously for several days. And indeed, my own home was blacked out for all but 90 minutes over 59 hours. The internal temperature of the house went to 6 degrees Celsius. I should point out, I have double glazed windows, a ton of insulation in my roof, a ton of insulation in my floor, insulation in my walls, and my house went to 6 degrees. So it was very cold. It was well below freezing. It was about 10 Fahrenheit, so maybe about minus 10 or 11 Celsius at times. Someone asked in the Q&A what a derate meant. One might have a forced outage of the full generator, meaning if it was 100 megawatts capacity, it could produce nothing. But a derate means that, let's say, a 100 megawatt generator was only able to provide 50 megawatts, let's say. So we'd say it was derated by 50 megawatts, just to clarify that question on the Q&A. We had supply problems, we had high demand. What was the reason for it all? Well, it's very obvious. It was extreme cold. And we could say it was a common mode cause of both the high demand for electricity and the failures in the infrastructure, okay? And this issue of common mode is very important because many of our historically used reliability assessment tools tend to be based on assumptions of independent failures, except in a particular common mode, a double outage of a transmission line, let's say, or a double outage of 2 generating units at a single plant. We don't tend to analyze common mode failures that affect tens and tens and tens of generators, and perhaps also simultaneously pushes up the demand. So this is a very important thing to bear in mind, that the cold was a common mode cause of what happened. Of course, it was a great inconvenience to me, but it far more fundamentally, it contributed to a number of deaths. I've heard up to 100, directly and indirectly. Directly because people literally froze or had hypothermia, and indirectly because the interruption of electricity caused things to happen that indirectly led to their death, for example. So what happened to prices? Well, as Perry mentioned, ERCOT is an energy-only market. It might be better to call it an energy and ancillary services-only market. It's similar to the Australian NEM and the Alberta market, but quite different to other US markets in that other US markets either have a capacity market or, as in California, a resource adequacy requirement on load-serving entities. So in the ERCOT market, in the Australian NEM, in the Alberta market, capital formation and contracting is on the basis about expectations of occasional high prices, together with most of the time prices reflecting something like marginal costs. In contrast to the Australian market, ERCOT also has a short-term forward day-ahead market that's very similar to other US markets. But it differs from other US markets in neither having a capacity market nor a resource adequacy requirement. And I would observe to you that that's not necessarily a bad thing. ERCOT has got along with it for a long time. The NEM has got along with it for a long time. It's not that it doesn't lead to prudent measures, prudent weatherization measures. And in particular, our market is sufficient to motivate summerization, I would point out. But it's, on the other hand, perhaps not fully capable of motivating winterization of our infrastructure. So that's something that I'll return to towards the end. As I said, we have no capacity market. Other US markets have a capacity market to procure capacity at multi-year ahead time frame, or, as in California, retail obligations. Some people have suggested that if ERCOT had had a capacity market, we wouldn't have had such a mess. In particular, capacity markets include penalties for not being available at peaks and therefore might have motivated winterization. But bear in mind that no one really expected these sort of winter peaks, so they might not have been motivated to do that winterization. Furthermore, it's also observed that capacity markets motivate firm gas contracts and dual fuel capabilities. Dual fuel might have helped, but I'll point out that the gas suppliers reneged on firm gas contracts on the basis of force majeure claims. So it's not clear that a capacity market would have helped, and it's also not clear that a capacity market would have been sufficient for a multi-day extreme event. We had extreme events for multiple days, and indeed the wholesale prices were at the offer cap of $9,000 US a megawatt hour for several days during the blackouts. There is a so-called circuit breaker that's designed to lower the offer cap, and indeed it's designed to avoid excessive wealth transfers. It was triggered, but it was ineffective, unfortunately, because the lower offer cap happens to be based on a large multiple of gas prices, and whoever was supplying gas at spot was selling it at a very, very high price. So it turned out the lower offer cap using the formula turned out to be higher than the higher offer cap. But the bottom line is that this circuit breaker never envisaged multiple hours, in fact, multiple days of prices contiguously being at the offer cap. It had in mind that there would be a few hours here and there where prices were at the offer cap. Having said that, those wholesale prices are not necessarily translated to what people pay. And indeed, very few end-use residential customers were exposed to these prices. There were a couple of news articles about people who were exposed through a retailer that's by the name of Gritty. Their situation seems to have been very unusual. There's only a few thousand, perhaps a few tens of thousands of such customers of Gritty in about 10 million customers in ERCOT. Having said that, though, many commercial and industrial customers would have been at least partly exposed to wholesale prices through either purchasing from wholesale or purchasing through a retailer in some version of an indexed price that's indexed to gas prices. Well, let me finish by suggesting in some way how it might be relevant to Australia. That Northern Hemisphere extreme cold is in fact a jet stream phenomenon. And as I'm not a meteorological expert by any means, but I understand that jet stream phenomena are less likely and less severe in the Southern Hemisphere. Having said that, the heavy recent rain in New South Wales was due to a combination of La Nina and the jet stream. So jet stream events can have big effects on Australia, but perhaps not triggering severe cold. But having said that, common mode phenomena, remember I said the extreme cold was common mode cause of a bunch of failures and the high demand. Such common mode phenomena are relevant to tight supply conditions, I would say everywhere. And for example, we could imagine a combination of widespread high temperatures, low wind conditions. This might be a problem for Australia, particularly after sundown, with a California duck curve type arrangement. If there wasn't an evening sea breeze on the coastal East Coast, then it would stay hot, all the air conditioners would be on, the sun would go down, and we would have a similar pretty serious problem. It might not last for several days, but it would still be a common mode phenomenon. And I would observe that our societal risk tolerance for those phenomena may actually be rather lower than the risk tolerance and indeed exposure of market participants. So in particular, market participants in ERCOT weren't really going to make the investment based on their own business plans, apparently, to do winterization, because on a roughly cost-benefit basis, it really wasn't worth it to them. On the other hand, for Texans, and I'll occasionally think of myself as a Texan, Texans as a whole, our risk tolerance for that sort of event is pretty low. It might not happen again for a decade or more or multi-decades, but I think we're going to want to institute things that make it impossible for a similar event to happen again. And that, to me, suggests a very important role for regulation and standards to handle such phenomena. That shouldn't be much of a surprise, and also is not a departure from the way we handle many things in the electricity industry. And for example, just to cite one particular example, it's somewhat analogous to low voltage ride-through requirements for various generators. With that, I would like to finish. There's a question that says, won't climate change, extreme weather repeat issues? So what will be done to address that? I think that's an excellent question. I'm not sure at this point what we're going to do. And I am very concerned about what I've described in a blog as ready, fire, aim. In other words, not really investigating what the cause was before we jump to making decisions and making changes. But it does seem, for example, that one of the biggest problems was the supply of natural gas. And my understanding is there are specific technical things to enable that to be dealt with. In particular, what happens is the water in the gas freezes, and that freezes the line. There are technical ways to deal with it. I think we could deal with that, and that would have allowed a much greater amount of natural gas, perhaps, to be available to the natural gas-fired generation plants. So those repeat events, could present problems again, but I think there are likely to be technical answers to how to deal with it. And then someone has asked, was nuclear power affected by the extreme event? There was a freezing of the cooling water on one of the four roughly 1,000 megawatt nuclear units, and that caused it to shut down. And again, I think we could argue that with a little bit more insulation around the water, they might have been able to deal with that issue. So with that, and with a partial answer to some of those questions, which might come up in further discussion, I'd like to pass it back to Ken.
Great. Thank you very much, Ross, for those really interesting insights. And just before I go on to introduce the two discussants who will be giving their own perspective on what Ross and Perry have just presented, just let me remind you that you can think about your questions and put them in the Q&A box, and we'll run through them immediately after our discussants have their say. So let me first introduce Dr. Liz Ratnam, who is a future engineering research leader at the Australian National University, where she's also senior lecturer in the School of Engineering. Liz holds an ongoing affiliation with the California Institute for Energy and Environment at UC Berkeley, and is a research leader in the Battery Storage and Grid Integration Group here at the ANU. Her research interests are in developing new paradigms to control distribution networks, with a strong focus on creating a resilient carbon neutral power grid. Over to you, Liz.
Many thanks, Ken, and I might just share my screen with some slides. Good morning, and many thanks for the opportunity to present today. Today, I'd like to reflect and contribute to the discussion by Fereidoon and Ross of preparing electricity networks for extreme climate events, drawing on the learnings of California and Texas, and a little bit more broadly in the Australian context. So first, I'd like to note that global energy systems are transitioning from large fossil fuel-fired generation to renewable sources, and the trend is set to accelerate over the coming decades. As a consequence, there will be a reduction in the synchronous generation that underpins operating paradigms for frequency and voltage stabilization in the grid. Frequency and voltage stabilization reduce the occurrence of widespread power outages in electricity networks. An element of the transition is the increasing adoption of distributed energy resources, such as rooftop solar, small-scale energy storage, demand control mechanisms, and electric vehicles. As DER adoption grows, global and electricity systems will demonstrate increasing levels of decentralization. This change is currently happening in Australia much faster than any other nation. As decentralization progresses, the challenge of managing two-way power flows from the grid to the customer, and from the customer with surplus rooftop solar energy to the grid, will upend existing paradigms for grid operators. Alongside changes to the energy mix are increasing impacts to the electricity system as a result of extreme climatic events, such as widespread bushfires, cyclones, flooding, and storms. A 2017 Deloitte report found that the total economic cost of natural disasters to Australia is growing and will reach $39 billion per year by 2050. With the rise of distributed energy resources, including rooftop solar, electric vehicles, and battery storage, and the retirement of coal-fired generators across Australia, there is significant uncertainty about future grid resilience. With millions of distributed energy resources, there is opportunities to potentially arise to improve grid resilience to extreme weather events, with generation co-located with electricity use throughout the distribution grid, removing the need for electrons to move from large-scale generators to the home. To fully leverage this opportunity, first, we must have situational awareness about how the grid is operating. That is, can we see the impact of the weather event on the power grid, including the distribution grid, through the physics of the electricity network? Can we see generators are operating as we expected? Can we see the poles and wires have not fallen over, for example? Next, can we operate the electricity grid in a way to isolate resilience issues? Does this mean operating the grid instead of one large electricity grid, but rather in many microgrids? So can we move from this large operating paradigm of the whole grid trying to address resilience events to breaking up the grid during these events so that we can improve the supply of electricity? And third, during resilience events, when generation availability is limited, how do we price electricity fairly so that we can reflect a fair price for all, from the wholesale market to the energy user? So as price during a resilience event, for example, when in Texas it was freezing cold conditions, is it fair to charge everyone the top price in the wholesale market during such an event when there really isn't much options for the market to bring more generation on board? So can we think about the suitability of this top price from a day-to-day normal operation to these resilience effects, and can we price it more fairly? And so a lot of these sort of trends and ideas reflecting on California, Texas, and going back to my own personal event, in 2007, we had in New South Wales this Pashabolka weekend where we had flooding, we had storms, and I personally had no power for four days. During that time, there were some customers with rooftop solar, and even though they were generating this electricity, they could not use it because the grid hadn't been designed to operate, allowing customers to go off grid or to share their energy across their streets. So for example, many poles and wires had fallen down, but there was many neighborhoods where they had all of the infrastructure intact. They had rooftop solar, yet they still had 4 days of power outages. So this really motivates thinking, I suppose, about distribution grids, how we plan and operate moving into the future in the context of preparing electricity networks for extreme climate events. And so that concludes my presentation.
Thank you very much, Liz. And now I'd like to introduce Anna Bruce. Dr. Anna Bruce is a lecturer in the School of Photovoltaics and Renewable Energy Engineering at UNSW, University of New South Wales. And Anna has research and teaching interests in energy policy, markets, regulation, renewable and distributed energy integration, and energy system performance analysis and modelling. Anna is an expert in the International Energy Agency's PV Power Systems Programs Task 13, PV Performance and Reliability, and Task 14, High Penetration PV and Electricity Networks, and leads the Australian PV Institute's Solar Mapping Project. So over to you, Anna.
Thank you, Ken. Yes, so thanks very much, Ross and Perry, for those really interesting accounts of what's happened in California and Texas. And Liz, your response as well, wholeheartedly agree with the importance and potential role for distributed energy as well. So I'm going to talk a little bit about the similarities and differences with between the NEM and the ERCOT and California as well, but also some of the learnings that we have been seeing from recent experiences in the NEM as well. And I should just also thank my colleagues at the Collaboration on Energy and Environmental Markets for various conversations that we've had about resilience and work that we've done on resilience and also specifically the recent events in Texas. So in terms of relevance to Australia, we have also had a number of recent extreme weather events of our own. There was the recent flooding in New South Wales that Perry's already mentioned, but we also had really widespread significant bushfires last summer, which is relevant to California, as Perry also mentioned, and certainly you could envisage what Ross referred to as a common mode failure associated with this kind of weather pattern of really extreme heat and bushfires. We are also, parts of Australia are cyclone prone, which is also relevant, I think, to Texas as well. But I think we really had our Texas moment when we had the islanding of South Australia, which you can see down here in the bottom right, some of the images there of the transmission towers that were blown over in that massive storm, triggering a whole range of failures of different generators and parts of the network. So this is kind of similar to those events that we were just talking about in California and Texas. It was also a climate-induced extreme weather event. Renewables were similarly blamed by some stakeholders for the failure of the system in South Australia. But there was also some failures of operational practice as well. So in terms of individual generators not being available to respond as they should have, and there were specifically some issues related to wind ride-through and how those requirements were actually being implemented. And yeah, I guess a lack of clarity around that, around those ride-through provisions. So some regulatory issues there and operational issues. Yeah, so that's our kind of Texas event. And then in response to that, we have had a range of market design activity and interventions that have occurred since then. So we have subsequently had the introduction of the retailer reliability obligation, which is designed in part to ensure that we do have sufficient capacity to ride through these kinds of events. So I think I wanted to mention one thing also about South Australia as well, just in terms of the ramping that we saw in California there. I believe that we already have comparable ramping in South Australia due to solar as well, but thus far we seem to have had sufficient flexibility to meet those ramps in South Australia. Yeah, as Ross mentioned, we have a similar market design to the ERCOT arrangements with a high market price cap. But differently to Texas, we do have a cumulative price threshold, which is designed to put a cap on the overall costs that might accrue when we do go to the market price cap. And I wanted to also reflect on the governance arrangements as well. So while we do have a similar market design, relying on that market price cap to drive investment, I think from a governance perspective, we have a different situation, partly because we have multiple governments involved in making decisions, including state governments. And we have seen governments in Australia being increasingly open to intervening in procurements, and also increasingly introduction of regulation, including to provide incentives for investment like the retailer reliability obligation. But I think also importantly in the NEM, we have the ability for any stakeholder to propose a rule. So it does allow multiple stakeholder perspectives to be involved in changing the rules as we deal with this increasing climate risks that we're seeing. What we've seen in Texas isn't the kind of event that is considered in our current planning framework, which does focus on how to deliver reliability at the lowest cost, and it doesn't consider those really extreme or compound events, which are really difficult to quantify and predict. And yeah, I think similarly and importantly, the value of customer reliability when you're talking about an event of that scale and over that time frame is also really difficult to quantify. So just a little bit more on how what we actually learned from South Australia and the recent bushfires, etc. So the AEMC, the rule maker in the in the NEM has recently recommended a range of changes to the NEM's security framework. So this includes new mechanisms to enhance resilience in the power system. And we are also seeing AEMO as well, bringing resilience and climate risk into the planning framework to account for extreme events. So there's an appendix in the ISP that specifically deals with resilience. So they do note in the ISP that the extreme events aren't considered in current planning processes, and that internationally good engineering practice rather than cost-benefit analysis is recommended for resilience planning. And I think also going to Liz's point about distributed energy resources, we are now seeing in Australia as well opportunities for networks to facilitate standalone power systems for communities or taking individual customers off grid. So yes, I guess there's a recognition that we need to consider how we can factor in resilience into our planning and operation. And then I also have another little image here from a report, a Royal Commission report into national natural disaster arrangements. And in that report, there's only one mention of standalone power systems and really limited discussion about electricity infrastructure. And I think just in general, there's a need to really acknowledge the intersectoral linkages, including fuel supply, obviously, as we saw in Texas, but just more broadly, critical infrastructure. And to consider the implications for communities if they lose access to not just electricity, but water and telecommunications and other things that require electricity. Okay, so this is a diagram from the AEMC's, an AEMC report that they put out after the South Australia bushfire, and it is interesting to see how they're seeing resilience, as part of system security, broadening that out to include resilience. And they do separate out security, managing credible contingency events, and dealing with non-credible contingencies as part of ensuring system resilience. And these indistinct events here are those kind of common mode or compound and unpredictable events there. And down here, they really highlight that there's a need for, a better understanding of those risks and new ways to manage those kinds of events. So in terms of options for improving resilience, I won't go into detail, but there's obviously a clear role for regulation. There's questions about incentivizing capacity, both through the planning framework and markets. Ross mentioned, capacity markets, etc. But still, there's a need for regulation there to ensure those generators are online. But overall, we do need to ensure that those options are consistent with consumer expectations and their willingness to pay as well. So I just wanted to finish by introducing these definitions here for resilience. So the top one is from the UN Office for Disaster Risk Recovery, the ability of a system to resist, absorb, accommodate, and recover from the effects of a hazard in a timely and efficient manner. So The second one is a C-grade definition, which AMO adopted in the ISP appendix. Limit the extent, duration, and severity of an event. I think that second definition is really focusing on the resisting the effects of the hazard, whereas that absorbing and accommodating, in the case of Texas with an event like that, it was regardless of how much, it would have been difficult to have enough, it would be expensive to have enough capacity to be able to manage an event of that scale. And, maybe we do need to consider how we absorb and accommodate the effects of a hazard, but considering community key needs in these kinds of events in terms of their energy services. And as Liz mentioned, there's certainly a role for distributed energy resources there, but also recovering. I heard an account that the Texas event, if it had gone to assistant black, it would have taken many weeks to recover. So obviously that capability is critical there. So yeah, I guess we're still working out the processes for planning for resilience, and but I think it will require engaging with multiple stakeholders and thinking across sectors and how they interact. So thanks.
Good, thank you very much, Anna. So now we might move to Q&A. And if I may indulge myself and have a first question from the chair. So Ross and Perry, it looks like that weatherization distinguished the Texas event over the California event. So has anyone done a calculation of how much infrastructure investment it would have cost to have weatherized the Texas system to cope with the recent event? And why might you want to do that? Well, you might want to work out how much incentivization mechanisms or penalties you might have to impose to stop this sort of thing happening again. So you might need to calculate how big the carrot or the stick might need to be by doing such a calculation. So maybe Ross, that's a question for you.
Yes, so there was a previous event I mentioned in my remarks. In 2011, there were a number of recommendations, and to answer another question on the chat, they were not made mandatory, something that perhaps in retrospect we might have regretted. But I also mentioned forensics, and I think it's important to understand that we publicly at least, we don't know how many of the asset owners in 2011 went on to weatherize or didn't, how much it cost them, and which specific pieces broke this time in the electricity infrastructure, whether it was the same as last time, and how much they cost, okay? I think it's clear that the natural gas infrastructure also failed. I find it hard to believe that the cost to do a bunch of weatherization would exceed billions of dollars. And if we do a rough estimate of value of lost load at $9,000 a megawatt hour times 60 hours times 20 gigawatts, you get about $5 million. People have estimated it closer to 15. The insurance losses are much higher, but I think many of those are not attributable to the electricity infrastructure. So let's start at 15, and let's say it's a once in a decade. These days we have 0% interest, so we could say $1.5 billion a year. I think it's, as a back of the envelope guesstimate, I doubt that it would cost more than $1.5 billion to fix all the things that got broken and weatherize them, okay? I just don't believe it, okay?
Right.
I will, however, say that winterization of sensors, and some sensors failed, is somewhat antithetical to summerization, meaning in the summer, you want to lose heat, you want to be out in the open, you want to cool them down, and in the winter, you want to put insulation around them. So I can see that this might be an annual event to put this, the winterization on and then take it off, but I still don't think it would have cost $1 billion. So I think Again, let me emphasize that we haven't done the forensics, we haven't done the cost benefits, but to take your drift, I think we'll find that we were penny wise and pound foolish on the weatherization. I think so. I think we would have been a lot more resilient to take up another issue with a relatively modest expenditure had we done some weatherization. Okay, so that's my admittedly back of the envelope guesstimation, but I don't think it's credible that it would cost more than $1 billion a year to do it.
Okay, great. Thank you, Ross. So now we might go through the Q&A, and there's quite a few. We might start with the ones that have been voted up most popular. The first one, I think Anna's addressed reasonably well, but other participants might have something to say. So this is from Ty Spartan, who asks, how might we pay for increased system resilience to extreme weather, and how would we get it authorised within the current frameworks in the Australian system, basically? So comments there from others. I think Anna gave quite a good answer before.
Well, again, in the ERCOT context, I think there's basically going to be two choices. Is there a regulation / standard for weatherization that's imposed by the regulator, or is there a specific carrot to do it? I think, frankly, a capacity market is too blunt an instrument if we can identify very specifically what were the things that were broken, and what broke 10 years ago. And if they were the same, it's going to be pretty obvious that they're the things that are going to break next time. And I think some direct, specific regulation on that matter would be the most economical way to do it from society's perspective. How to pay for it, whether you impose that as a regulation or you throw some money at it, this is a question of the polity and the public taste, right? So I don't think I have a strong opinion on that. But before we get to that, we should figure out what we need to do, right? And then think about how to fund it.
If I may, let me just pitch in a little bit. In California, the regulators believe in regulation. It's very opposite of Texas, where markets are supposed to solve all the problems. Here, when the regulators see a problem, or the governor sees a problem and tells the regulator to fix it, regulation is imposed. And so it's a very top-down mechanism. As an example, I think California is going to install over 1 gigawatt of storage between now and August, where we think we're going to have, hot summer weather. And the other thing that we do a lot of things through regulation in California. Again, there might be we might be on an extreme end from where Texas sort of handles things, where everything is sort of left to the individual, whether it's individual household, like Ross, who has an insulated house, and his neighbor probably is not insulated at all. In California, houses, the building codes in California are among the most stringent anywhere. And California Energy Commission passed the building code in 2020, which requires all new residential homes to be essentially zero net energy. And this is going to be extended to commercial buildings. So in California, the way we handle problems is through regulation, and maybe heavy-handed regulation. So, there's space for discussion which way is the better way to go. But, if houses are better insulated, well, then, maybe these extreme weathers would not have as big an impact on the network. I don't know. What do you think, Ross? I
think it's absolutely true that although we've predominantly been talking about weatherization in the context of the electricity industry, it is likely to be very cost effective for houses to weatherize houses. And you're absolutely right, Perry, that there is Texas is perhaps the antithesis in terms of regulation of housing. But if we invested in better insulation, it would help in the summer and it would help in the winter. So it would seem to me to be something that would be likely cost effective to ameliorate the effects of extreme weather. I'll add one more thing to that. California duck curve, when you translate it to Texas, we don't have a lot of solar yet, but Texas is very heavily driven by air conditioning, which tends to peak in Texas at about 6 p.m. Prevailing time in the summer, 5 to 6 p.m. as the sun is going down. If we had better insulation and more thermal mass inside the house, instead of blowing a huge amount of money on chemical batteries, as rich states like California and rich countries like Australia seem to do, we could instead spend a modest amount on insulation of houses and increase the thermal mass and pre-cool to better use the solar and avoid the duck curve. So I absolutely agree with you that there are smart things we can do with weatherization that I personally think would be a lot smarter than massive build-outs of chemical batteries, as apparently proceeding apace in both California and Australia at huge cost, I would say. And I'll make a very sarcastic remark about California. The regulations in California drive up the cost of electricity so much that's charged at very high retail rates, as they are in Australia. But it's not such a problem because all the homeless people who are driven out of houses because they can't afford it aren't buying electricity anyway. So it's not a problem.
So let's move on to some other questions. The next few, I think, have been answered more or less through in general discussion, but there's one here that touches on exactly what was just being discussed, which is from Mark Byrne. So Mark asks, how do we find the right balance between bulk system and local energy supply systems to maintain system resilience in the face of increasing severe weather events? And maybe we need to work out what is meant here by local energy supply solutions, whether it means a household with batteries, whether it means, I don't know, suburban scale batteries or other storage mechanisms, but that's an interesting discussion point.
If you don't mind me jumping in, sort of tying it back to the other question, if that's okay. Just thinking through from a utilities perspective, right? We tend to do 5 to 10 year planning horizons when we invest in our network, and we consider things like metrics, SAIDI, SAIFI, MAFI, a bunch of them. When it comes to resilience, how does a utility sort of plan for that? Like we need some metrics, right? And we need to have in that planning stage when we're thinking 10 years ahead, how do we strengthen our system? And so, you know, there are opportunities to think about it in different ways to what we've traditionally done, but really I think what underpins not only the regulatory framework and things like that, but also what are the business processes? How does a utility incorporate and compensated for hardening the network, giving the utility that opportunity to think ahead in that planning, that early stage before events would be really important. So I don't know if that touches on this question as well as the previous, but
Elizabeth, I think it does, and I'd like to make a comment. One of the reasons why my house was blacked out for so long, effectively continuously, was because I was on a feeder that was neither utilized as under-frequency load shedding, which is an in extremis last ditch to prevent a cascade. There's 25% of ERCOT load is on under-frequency load shedding. And a number of other feeders also supply hospitals. In other words, it's a feeder with critical load. When the ones that were left over, such as me, were stuck, right? Now, technological developments or technology like automated remote reconfiguration of distribution feeders, I think would help in a number of dimensions. You could move my load to a different distribution circuit. You could move off some of the non-critical load that happened to be on a feeder that a hospital was on and apportion the blackouts. If I had power 2 or 3 hours every 12 hours, I would have been pretty happy. I could have got my house warm. I could have charged my devices. So I think that's a really potentially a good example of a resilience enhancing ability to control when we're in these extreme situations, how to share it out. And so I think that comports exactly with what you're describing. And I think it could also, for example, help with the rooftop solar that is switching off when it's not connected. Well, I could try to reconfigure my feeders so that I'm getting as much benefit from the solar, the connected solar, for example, right? So I think it would help with resilience along multiple dimensions. So I think there are some technological issues like that. That's out in the poles and wires. So it's going to be a rate of return regulated issue. I know Australia's had a lot of concern about gold plating, but it strikes me that that's the sort of thing that could be very valuable to improve resilience for these sort of events.
Thanks, Ross. Yeah, completely agree.
Okay, so let's move on to some other questions. So speaking of poles and wires, there are a number of questions that talk about the issues relating to the distribution networks and the power transmission networks. Whether there are things that can be done to improve the reliability of elements of the grid, but also in terms of people on the fringe of grid, whether to move them off grid and make them locally self-sufficient to reduce these sorts of issues. So does anyone have any commentary about these sort of transmission and distribution network issues?
Well, I can make a comment that is maybe California specific, but we've had these because of extensive fires that we've had. The utilities are now have something called safety, I forget some acronym. Basically, when there's a high risk of fire in a given neighborhood, they just shut off the power to everybody. Because if they don't, and fire is caused by the spark in the distribution lines, utilities get sued. And PG&E, as you remember, was in bankruptcy protection for a couple of years. They just barely came out of it. So this is a particular thing. It has nothing to do with scarcity of supply. It's just that when you have these extreme weathers, again, we're talking about extreme weathers, we just have the fire season that essentially doesn't end. It's like year round. We have drought and fires almost the whole year. And so that is a big problem. And it's driving people to install solar and battery and essentially be able to self-island from the network so that they can manage, because these fire safety system shutoffs or whatever they're called, they don't last 2 or 3 hours. You know, when they shut off the network, the utility crew has to go and check every circuit before it's re-energized. So people are left without power for 2 or 3 days. It has nothing to do with supply and demand. It's just a local, again, it kind of goes back to Ross. You know, we probably have better systems to be able to reconnect people faster. Otherwise, a lot of customers are just going to become off grid because they just say this system is not reliable enough and I can't survive with, you know, on that kind of a service. So that's an issue. It's a little separate perhaps from everything else we've been talking about, but it's very serious in California.
And it's certainly true in Australia where fringe of grid customers experience more outages than others, and they're also in fire risk areas more often. So yeah, that's common experience, I think. So let's move to a slightly different topic. This is from Tim Ryan, who's back on the question of compound event failures, and he asks, don't we need better systems to shed load rather than the current whole of load or substation approaches? For example, pre-planned commitment to voluntary load shedding on non-essential loads, and that enables customer choice to help with this issue.
So there are programs like that in Texas, but the amount of load shedding required, which was 20 gigawatts, far exceeded the price responsive demand, far exceeded the emergency response demand that has pre-agreed to do this. So I'm not disputing that all of those things are valuable. It's just that the level of curtailment went beyond what any of those levels allowed for. But to the point, being able to pinpoint individual loads and switch them on and off, I think would be valuable even in that context, by being able to share the pain more equitably.
Mm-hmm.
I guess a short comment, feedback comment is that I made that point. In the case of California, the shortages were about an hour or less, and 1 gigawatt in roughly a 40 gigawatt system at the time. So batteries could have helped, electric vehicles, all the Tesla owners got a signal telling them, please don't charge your car during these hours. It wasn't mandatory, but if you had an electric car, you would have seen that signal. So 1 gigawatt for 1 hour, piece of cake. But 20 gigawatts for 4 days, entirely different problem, right, Ross? So you need something massive. Electric vehicles are going to run dry. Your battery's going to go dead. I mean, it's just a totally different scale. So that's another issue. How long are these weather-induced events? Are they a few hours or a few days?
Okay, so just looking at the time, we've got time for maybe 1 or 2 more questions. There's a question from Rama G. What approach is taken in the US to value the consequences of these kind of events? And given what we know about societal costs far exceeding the tolerance of the participants. So it's this, cost-benefit analysis, and it's the tolerance settings that are important in working out future solutions to these issues. Maybe you could comment on that.
Well, I think it varies from state to state. I think what happened in Texas in February would not be deemed acceptable in any state. As to what the exact regulatory responses would be in different states, I think they would vary very significantly from state to state. But there are several bills proceeding in the Texas House and Texas Senate that are likely to mandate, enforce, or otherwise change requirements for resilience, for weatherization, for all sorts of things. So I think it's largely is going to happen legislatively and through the state-based regulators, I would guess. But maybe Perry would have a better thought on that.
Well, I will give you an example. Those of you who've been around long, like I have been, Ross, we had a major crisis back in 2000, 2001. It's known as the California electricity crisis, where we had massive blackouts for many days. It wasn't because of supply and demand. It was mostly because of Enron and manipulation of the market. But anyway, at that time, we had a governor, a Democratic governor, whose name was Gray Davis. And believe it or not, the poor handling of the electricity crisis lost him his job. There was a recall election, the first time in California history, a governor in midterm was thrown out of office. So when you say what happened, if you talk to Ken, this guy, Gray Davis, he will tell you what happens when the lights go out for an extended period of time. Now in Texas, the governor hasn't lost his job, and I guess he successfully has blamed other people, and maybe he's not to be blamed. But in California, the governor just mishandled the crisis poorly. His messaging was wrong, and voters had enough and threw him out of office, and that's history. This time, the governor was much more proactive, and of course, the crisis was limited. But as Ross pointed out, it depends on the state. It depends on how you message the crisis and how well you handle it, and a number of other issues. But it varies from place to place and how bad the situation is. But I think the ERCOT has been pretty serious financially, economically, and politically, I would think.
And Ross, would you say that that even if there is no immediate political fallout from the event, that politicians will now be looking very carefully at how they craft future policy and future messaging?
Without a doubt. And there is everything from coherent proposals to completely spurious proposals on the table. So as to what washes out and to what extent science and engineering is used as the basis for the policy is an open question, right? There are, for example, proposals in the Texas Senate and House that, as far as I can tell, are simply aimed at whacking renewables, but with no discernible scientific or engineering relationship to the problems, but yet they are there as bills. So I think there is, like everywhere, a serious problem in a disconnect between science and engineering based solutions and what gets translated into policy. And I think we need to try to fix that. But I plead guilty that I have not been down to the House to protest against their crazy bills, right? So mea culpa on that, but somehow we need to inject science and engineering into that policy decision.
Right.
Good point.
And as Anna pointed out earlier, we've been there, done that in South Australia, and exactly the same whacking of the renewable energy industry was done here as well. Well, I think now is time to draw things to a close. So thank you, audience, for all your questions. There are quite a few questions unanswered. We can direct some of those that you've asked us to direct to specific people and see if we can answer them offline. But otherwise, thank you for your questions and your participation. So it only remains with me now to thank, first of all, Erica and Ariel for joining with the ANU on this State of Energy Research webinar series. And of course, to thank our participants, Perry Shoshani, Ross Baldick, Liz Ratnam, and Anna Bruce for your great insights into these questions, which are still open and which we still need to be concentrating on the answers for into the future. So thank you all very much.
Thank you.
Thank you.
Good night.
Thanks, everyone.
Pleasure.
Good night in the United States.